day, another class in chemistry with your Dr. B, your chemistry lecturer. Today we are going to look at the Bronsted. We are going to look at the Bronsted Lowry Bronsted Lowry theory. The Bronsted Lowry theory. Bronsted Lowry theory. We're going to look at that. Do not forget, as part of your contribution to what I am doing here, you are going to assist us in liking, in subscribing to our YouTube channel. Do not also forget to share. It's very important. Share these lectures, share this YouTube channel to your friends, also to your colleagues and your groups, so that they can also subscribe and be part of these lectures we're having in chemistry, if you really appreciate what Dr. B is doing. Now, do not also forget to leave your comments. Even if it's a question form, we'll answer. Do not forget also that I have a Facebook channel, a Facebook page, Dr. B Chemistry Classes, and go there too to subscribe, to follow and share that page as well with your friends, colleagues, and also your groups. To like and to leave comments there as well. Now we are going to discuss Bronsted-Lowry theory. Now the names sound a little bit strange, but this is an aspect of chemistry. Now before I go into what Bronsted-Lowry discusses about acid and bases, it's important for me to let us know that we also have a theory we call the Arrhenius theory of the acid and base reactions. Okay, so this Bronsted-Lowry discusses acid-base reactions. We also have Arrhenius theory that discusses the acid-base reactions. But what does the Arrhenius theory discusses that brought about the Bronsted-Lowry? Now, the Arrhenius theory simply says that acids, okay, are those particular species or substances that will produce a hydrogen ion, which is a proton, as the only positive ion, but it must be in solution. Underline that. It must be in solution. That means that species must dissociate in solution to generate what? A hydrogen ion. And for a base defined by Arrhenius, he said a base is any species or any substance that will definitely dissociate and generate a hydrozonium ion, which is an OH minus, when in solution. The point of emphasis here is that both an acid and a base will only be defined on the basis of the fact that they will produce a hydrogen ion, which is a proton, or as a base, a hydrozonium ion, which is an OH minus group, in solution. That is what Bronsted-Lowry, though agreed, but said there was a limitation to that definition. And that brings us to Bronsted-Lowry. He said, with that definition of Arrhenius, it means that for you to define an acid-base reaction, it must be done in the presence of a solution, which is water. That means you cannot say that a particular species is an acid or a particular species is a base, except if it can produce a hydrogen ion or a hydrozonium ion while in solution. He said it must not necessarily be in solution. And that is why Bronsted-Lowry theory of acid-base reaction simply look at an acid and bases on the basis of proton donor and proton acceptor. So if you look at the Bronsted-Lowry, it believes that what you call an acid is what will only, a species that will do what? Will be able to transfer a proton, which is what? A hydrogen ion. It must not necessarily be in solution. That is what Bronsted-Lowry says. And that for a base is that which does what? Accept a proton from an acid. That means that base must also possess at least one lone pair of electrons to be able to accept that particular proton. So to Bronsted, when he said an acid, it means it donates, species that donate a proton, okay? And when we said a Bronsted Lowry base, a species must accept a proton. And if a species will donate a proton or another will accept a proton, defines what acid-base reaction is. It means that it must not only be producing hydrozonium ion or hydrogen ion while in solution. So that in solution is what Bronsted said no. Bronsted believed that if we decide to look at acids and bases as being species that generate hydrogen ion and generate hydrozonium ion while in solution alone, then there are still some reactions that are acid-base reactions that will not be considered. Let us take an example. Let's look at this reaction between ammonia and HCl. Let us look at this reaction between ammonia and HCl. They are all gas reactions. Okay, this will give you NH4 chloride. Okay, it will give you NH4 chloride. Now, if you take a look at this reaction, there is no water in this reaction. So, from the Arrhenius point of view, this would not have been an acid-base reaction. But from Bronsted-Lowry, this is an acid-base reaction because you can still define any of these species as acid or bases on the basis of proton donation and acceptance. Let's see if it is true or not. Now, if you take a look at this, you will notice that if we take a look at the Lewis structure, you will see that this is ammonia. This is ammonia with lone pair of electrons. And this is HCl. This will give you this compound you have here, which is ammonia. You can see that. That means that this HCl, the HCl donates. It donates this hydrogen to the lone pair of the ammonia. And then from here, you have it in this form. You can see that from this definition, you can term this as the Bronsted acid. So this can be termed the Bronsted-Lowry acid. Why this can be termed the Bronsted-Lowry base? This is because the HCl donates a proton, which is a hydrogen ion, to what? To the ammonia, and the ammonia accepts it. Ammonia possesses lone pair. You can see this. These are lone pair of electrons. So the ammonia possesses lone pair of electrons, and it also has the tendency of accepting the hydrogen ion, which is the proton from this. So since this donates is the Bronsted-Lowry acid, since this accepts with the presence of a lone pair, it is the Bronsted-Lowry base. You can see that there is no water involved in this reaction. If we take the Arrhenius definition, it means that this is not an acid-base reaction. But from the Bronsted-Lowry theory, this is an acid-base reaction. And the Bronsted-Lowry theory became of advantage over the Arrhenius because it can be used to explain acid-base reactions in every type of solvent, not only water, and also in gas reactions. So both in gaseous reactions and any type of solvent at all, you can be able to determine what an acid-base reaction is in such a reaction. Now let us take a look at another type of an example. Now you can also have another example that will describe the Bronsted-Lowry theory, and you have something like nitric acid and water. Now, if you have a nitric acid and water, HNO3 plus water. Okay, so we expect it to give us NH3 plus NO2. Sorry, 3. You can see this reaction. Now, forget the fact that there is water here, but this is just to prove the fact that whether with water or without water, the Bronsted-Lowry theory says that you can be able to have an acid-base reaction, but not necessary with water. So now, if you take a look at this reaction, for example, you will see that in this reaction, there is increase in the number of hydrogen here. That means that the nitric acid decides to donate this hydrogen to this point. Hence, you could have this. See, so there is a donation of a proton to this water, and then you have the hydrozonium ion, which is now an acid, and this is now with this, it means that since this donates, this now becomes a Bronsted-Lowry acid, and this becomes a Bronsted-Lowry base. That means you can possibly find a lone pair of electrons in this water, and that tells us the fact that Bronsted-Lowry theory believes that water is neutral. Therefore, water is amphoteric. So if water is amphoteric, because he believes that water as it is amphoteric. And if water is amphoteric, it means that it behaves both as an acid and as a base. So here, it is behaving as a Bronsted-Lowry base. Okay? So you could see that this donates to this, and water serves as a base to form this. In as much as there is a transfer of a proton, then we can define that as a Bronsted-Lowry acid, and then the one that accepts the proton as a base. Now let us see where water will now also behave as an acid. Now if you take a reaction of ammonia, let's say you have ammonia and water, this reaction will give you NH4 plus OH. Now if you take a look at this reaction, you will notice that this is increased by 1 hydrogen. So it means that there is a donation of a proton from this water down to this. It accepts. Remember that of course ammonia is having a lone pair of electrons. So in this case, it accepts the hydrogen that brings its stability here. Okay, so the hydrogen brings its stability here. So ammonia at this instance become what? Our Bronsted-Lowry base. So this now becomes our Bronsted-Lowry acid, and this one becomes our Bronsted-Lowry base. You see this? So water behaves as a base, water also behaves as an acid, and you could see this shown here. So water behaves as a base and water behaves as an acid. That makes water amphoteric, just like what Bronsted-Lowry theory says. So the central idea here is the theory of Arrhenius concerning acid-base reactions is not complete. In short, it's not complete. Believing that it's only when you have species in solution that gives you hydrogen ion and hydrozonium ion as the only ions in solution is not complete. That even away from water, which is well recognized by Arrhenius, you can also have other solvents that can act on species and donate protons and accept protons that makes them Bronsted acids and bases. So today, I want us to know that it is not only when you say that a species dissolves or ionizes in water to give you hydrogen ion that is an acid, or a species dissolves in water to give you a hydrozonium ion that is a base, that it goes beyond that. According to Bronsted-Lowry, it goes beyond that. It must not necessarily involve water. a solution like water, any other solvent at all, can make a reaction an acid-base reaction. Okay, so you can possibly may not even have a solution, a solvent, it might even be gases, and you could have that reaction as acid base. Once that particular reaction shows that one has a lone pair electron and can accept proton, and one can possibly donate proton, it simply defines what an acid is, what a base is. I'm sure you enjoyed today's lesson. You have learned something so interesting as far as Bronsted-Lowry theory is concerned of acid-base reactions compared to the Arrhenius theory of the acid-base reactions. Do not forget to like, do not forget also to share, do not forget to subscribe, and especially share with your colleagues. Go to my Facebook page, like, share, and also do what? Follow. And most importantly, do not forget to leave your comments in form of answer questions. They will all be attended to.